Welcome, ladies, gentlemen, and everybody in between. My name is Gregory Szep, and I'm currently talking to you from my hometown of Vienna, and I will be talking to you about the inference of bifurcations and differentiable continuation methods. I'm lucky enough to be supported by King's College London and Microsoft Research Cambridge, and my grant is coming through EPSRC. So without further ado, let's begin. I will begin by talking about bifurcations and how to calculate them using bifurcationkit.jl. Then I will move on to parameter inference and what is currently being done using differential equations in Flux.jl, and why we should use bifurcations as targets in the first place. Then we'll move on to the design of the semi-supervised cost function, its motivation using normal forms, and how to ensure smoothness and differentiability, and hence compatibility with one of Julia's autodiff frameworks, zygote.jl. We'll move on to then an example of model synthesis and optimization using Flux.jl. Finally, we'll conclude by me showing you the repository, what the current issues are in sharp edges, and where we want to be in the future, what the roadmap to that could look like. What are bifurcations and why should we care about them? I've brought up the definition here. So bifurcation points are locations where small smooth changes in some control parameter result in qualitative or topological changes in system behavior. And there are many different types of bifurcations, but I'm going to show you just two examples just to give you a flavor of what qualitative or topological change actually means. Suppose I observe a steady state U at some control parameter P. Looking at the bottom left-hand part of this plot, where at a low value of bifurcation parameter P, we have a low value of steady state U. As we slowly start increasing the bifurcation parameter, the steady state also starts to increase up until we reach this black dot, which is known as a saddle node bifurcation, where the steady state at that value disappears. If we keep increasing the value of the control parameter, then suddenly the steady state will jump to the upper branch. That is known as a catastrophe. And as you continue to increase P, it also increases U slowly. This is an example of a switch behavior where the low value of U can be considered the off state and the high value of U can be considered the on state. And many different switches can be described using this model. For example, in biology, where a certain immune response could be activated via concentration of a particular white blood cell in response to the concentration of a particular pathogen. If we now lower the value of P starting in the upper branch, we actually transition to the off state at a lower threshold of P. And this is a kind of robust behavior that we would want in a biological switch, where even after the immune response is turned on and the concentration of the pathogen decreases, you don't want the immune response to turn off at the same threshold. This way we are sure that the pathogen is completely cleared out of the system before the immune response is turned off. This feature of having different transition points between states, depending on whether you're approaching from the on versus the off state, is a general phenomenon known as hysteresis. It can also be found in magnetism. Along the x-axis, we would have external field changing the magnetization on the y-axis of the magnet itself. We can also look at the saddle node bifurcation from the perspective of the geometry of the underlying state vector field that generates the motion towards the steady states. What does that actually mean? In this example, if we just place a single dot anywhere along the plane of that state space field and then follow the arrows, we just get led off the plane. So there is no stable location where the state can settle into. And that represents the cuts seen on the left-hand panel, where we can see that nowhere along the cuts do we see a steady state intersecting it. If we move the dashed line towards the saddle node, we can see that the state space has been pinched. The arrows now points towards the location that moves us along a ridge. And the dynamics doesn't quite stop at that location, but it slows down. However, just after the bifurcation point, that point splits into two. One basin of attraction you can see in dark blue, and another saddle node, which is seen in bright blue. And that saddle node attracts in one direction, but repels the dynamics in the other direction. And as we increase the bifurcation parameter, that pushes apart the saddle node and the stable basin. And we can see that the saddle node is responsible for pulling in the dynamics in the vertical direction, and then pushes the dynamics outwards in the horizontal towards the stable basin. Another bifurcation marked with the black dot here is called the pitchfork. That is a location where the system has to make a decision whether to go along the upper branch or the lower branch. One can describe cell differentiation cascades this way. As an organism develops, the stem cells are exposed to different concentrations of proteins in their environment that prompt them to differentiate into different subtypes. For example, in this case, the upper branch could represent a threshold concentration of a particular chemical to differentiate a stem cell into a muscle cell. Whilst when the chemical is not present, the stem cell differentiates into a nerve cell, represented by the pathway taken if we were to go along the lower branch. We can again look at this from the perspective of field geometry. Taking a slice at a low value of P intersects the single steady state, which generates a single basin of attraction where all the vectors pull us towards the blue dot. Just before the bifurcation, again, the field is pinched in such a way that it slows down the dynamics. Just after the bifurcation, we can see we've split into three different points. Two attractors either side of a saddle node. You may have noticed a general pattern here, where you cannot create a stable location without generating an unstable location at the same time. This is the same reason why you can't really dig a hole in the ground without generating a pile of rubble next to your hole. So for every minimum, you have to create a maximum. How do we actually calculate bifurcations? First, we write down a hypothesis as a set of parameterized differential equations. So let U be the observable states that we're interested in. There's a time derivative del t on the left-hand side, and then a vector function, f, which is parameterized by some unknowns theta and some known bifurcation parameter p. F can be as arbitrarily complicated as you want, space, time derivatives, it could be a neural network, whatever, as long as it outputs a vector that is the same dimension as the state space. So first we choose an initial guess, u0 at p0 of the steady state, and we use that as an input for the parameter continuation method. In this case, we're using the lovely library written by Romain Welz called bifurcationkit.jl. And as you can see, after the initial guess is converged using some Newton iterations to the actual steady state, we can then use a series of predictors and correctors to determine what the series of steady states is along the bifurcation curve. Dark blue shows us that the states are stable, and light blue tells us that the states are unstable. So the only places that the system can go is along the blue lines, and in the region in between -1 and +1, the system is known as bistable. In order to detect the bifurcations, we need to investigate the determinant of the Jacobian. What is the determinant of the Jacobian, and how will it help us? If we remind ourselves, the determinant of a matrix is the product of the eigenvalues, and the eigenvalues of a Jacobian represent whether a system is attracted to a local basin or repelled from it. So it's negative if it's attracted and positive if it's repelled. And the product of all of these signed eigenvalues will change sign if one of the eigenvalues changes sign, or one or more. So in this particular example, we can see that the determinant crosses 0, and I've shown where the determinant changes sign by marking it from going to dark red to a light pink. And you can see in the region where there's one unstable branch in between two stable branches, that's where the determinant crosses 0 and then flips back around and then changes sign back to being negative. And the locations where the stability flips is marked by black dots, and those are the locations of the bifurcations. So why use bifurcation points as targets? In the past couple of years, backpropagation through differential equation solvers has been a breakthrough and allowed scalable parameter inference against targets but mostly in the spatiotemporal domain. As illustrated here, this inference run is done in the time domain, which is shown in the very left-hand panel, where the model output, shown in dotted lines, is attempting to match the data, which is shown in solid lines. Now, if we represent the same information in state space, shown in the central panel, we can see that plotting one component against the other yields a spiral, which is generated by an underlying vector field shown on the right-hand panel. And it is actually the geometry of the vector field that generates the dynamics. So the problem is that collecting spatiotemporal data can be costly, and especially if you want it at high resolution. And oftentimes the data contains over-constraining information. So for example, in biology, you often report data in arbitrary fluorescence units or other variables that are not directly related to the underlying states that generate the mechanism, but only proportional to. So you can scale and shift your data arbitrarily. In addition, we can show that actually the dynamics can be more generally described in state space and in terms of state space structures. And we have previously shown that bifurcations actually define these structures. So if we're going to take anything away from this, is that I want to say that whilst observations in life and social sciences are becoming more quantitative, it is also important to design machine learning tools that accept qualitative inputs. And that allows the approaches to meet in the middle. Let's talk about the semi-supervised cost function that allows us to make bifurcations and put them in the locations that we want. We will use a minimal model that can span the space of saddle node bifurcations. And it has one parameter p, which is linear, and then two unknown parameters which will optimize θ1 and θ2, which pre-multiply the linear and cubic terms of that equation respectively. We note that the determinant, curvature, actually maximizes around the locations where bifurcations are about to happen. And if we notice, just before they happen, it's very sharply peaked, and then it crosses zero, and that's exactly what we want. Next, what we want to do is we want to move the bifurcations to the respective target locations marked by golden lines. And once we've done that, we call that convergence. Now, luckily, using this lovely little reference here, we can calculate the determinant curvature analytically. So for any given f, we'll always have a formula that is defined for all u, all p, and all theta. What is left over is the bit that basically pushes our bifurcations to the correct location. Let's call that the supervised likelihood term, which you can see I've chosen an exponential form that is close to 1 when the bifurcation locations match, and then exponentially fall off if they don't match. There's an additional term in the exponent which biases the supervised likelihood towards locations where the determinant is close to 0, which is exactly what we want. So in order to get the cost function from the likelihoods, we need to take the negative log of that. And in addition, what we want is to only select the locations in the UP plane that satisfy the bifurcation line, which is found using bifurcationkit.jl. Note that both of those functions inside the integrand are analytical for all u and p, and in order to calculate the region of integration, we need to use bifurcationkit.jl. I'm just going to move my head to the side so you can see that we are actually integrating over the whole region u and p. Once we have the cost function and we would like to optimize it with respect to theta, of course we need its gradients with respect to theta. So what we're going to do is just apply the gradient operator with respect to theta to the cost function. And we find that, firstly, not only is the integrand a function of theta, but also the integration region is a function of theta. So as an example, here I show you the integration region for a particular pitchfork. And if you change the parameters theta, the region of integration will change. And as a result, we need to take that into account, the fact that the region changes. So there's a velocity field marked in blue, which I'm going to call del UP by del theta, which will pop out of the chain rule here. And it is indeed what you get. So when you apply the general Leibniz rule, absolutely stunning, you get it popping out right there in blue. What makes it even better is that there's an explicit formula in terms of inverses of Jacobians. All of this can be analytically evaluated, at least in principle. Now we know that this is differentiable, we can be certain that it is compatible with zygote.jl. And if we want, we can also supply our own custom adjoints to help it differentiate this beast. How do we implement this in an actual algorithm and make sure that it's smooth and there are no sudden jumps or waiting times between iterations? Outline to you the inputs and outputs first. A function f, which is known, and it takes as an input an n-dimensional state vector, scalar parameter p, target bifurcations in a particularly known region between p-min and p-max. Finally, you add a convergence tolerance to terminate your procedure at some point. The optimized theta will live in a different dimensional state space, Rm, and they must satisfy the targets. So first we pre-calculate all of the analytical forms that we can. That includes the Jacobian, the determinant of the Jacobian, the curvature of the determinant of the Jacobian, and the velocity field of the integration region. Next, we need to initialize our first guess of u0. Remember in the previous slide, we needed a particular initial guess in order to first run the continuation. And an initial guess for the optimal theta as well. Let them be just random numbers. And we should also initialize some hyperparameters, which I'll collect in an object called beta. This will contain things like arc length step, Newton solver parameters, and other things that the algorithm needs in order to be adaptive to the problem at hand. The main optimization loop will run bifurcation kit.jl to get the steady states. Let's call the collection of those steady states omega. And as you can see, we overwrite the old u0 guess with the new u0, which will certainly be closer and almost on top of exactly what the steady state should be. Next, what we do is we use the integration region that we've calculated, the targets x, the determinant of the Jacobian, the determinant curvature, and the velocity field all together to compute the cost gradient. And then we use the cost gradient, here depicted by del L, to update the parameters. Note that here, the two steps that allow smoothness between iterations is the adaptive hyperparameter update. This means that, for example, if theta changes the system such that the steady states occupy a much larger range, the arc length step will adapt, it'll increase so that we converge in the same number of seconds each time we iterate. So let's give this a spin. Let's look at these two minimal models, one of which I described earlier, where p is linear. Now, if we flip the locations of p and theta1, we end up exploring the space of pitchforks. Let's call that the minimal pitchfork model. And if we look at these two models and optimize thetas respectively, we find the following. So if we look at the left-hand panel, we can see that bifurcations emerge as curvature is maximized, and boop, they appear, and then finally they settle down at the location of the golden lines, which are where the targets are. In the minimal pitchfork model, on the other hand, we just have one target, and the bifurcation gets pulled towards it from the side and then wobbles around it for a little bit. I've increased the momentum here. This is momentum gradient descent, just to illustrate the fact that the basins for the minima of convergence are quite wide. This runs on the GPU, so as you can see, the iterations converge within a couple of seconds, which is nice. Here's another example known to the synthetic biology community as the genetic toggle switch. In this case, it has 7 parameters, theta, and 4 components in U. So U lives in a 4-dimensional space, and here we're just plotting one of those components. And as you can see, we can tune the bifurcations to occupy any particular location we want. See what's happening behind my head. You can see that the bistable region that I specified is somewhere in this region here. And convergence. This is an older version of the code, so hence why it's a little bit slower. We can also investigate what the equivalent models are in the theta space. So because our minimal models just have 2 parameters, we can simply plot the cost function explicitly in a contour plot. On the left, we have the minima of the cost function represented in dark purple and the maxima represented in bright yellow. On the right, I've sampled the space of all possible models which come from different values of theta1 and theta2. If we focus in on the dark purple basin, we actually find that that outlines the topologically equivalent models, where the bifurcations have come into the field of view, and we've left out all of the models that are just purely unstable or purely stable branches. A subset of those topologically equivalent models are the geometrically equivalent models that actually match the locations of the bifurcations where we've specified the targets. However, whilst the models can be geometrically equivalent, they can be kinetically different, which means that if we go back to the time domain, not only could the transients be faster or slower, but the actual locations of the steady states could differ. But the locations of the bifurcations are the same. If we want to pick out a kinetically unique model, then we simply choose a point along the set of geometrically equivalent models here shown as a cubic white line. You may have noticed that the topologically equivalent models actually form two basins, one of which describes the pattern of stability stable, unstable, stable, which gives rise to bistability and a hysteresis curve. The other basin, on the other hand, is unstable, stable, unstable, which basically just gives rise to a region, an island of stability in the middle, and then nothing else. We can apply similar thinking to the minimal pitchfork model, where we can see that the geometrically equivalent models lie on a cross, which is a subset of a basin that outlines the topologically equivalent models. So now that we've established a proof of concept of what we're trying to achieve, where are we going to go from here, and what would the eventual goal be for this particular project, the repository first? We've applied two minimal models that help us explore the space of pitchforks and saddle nodes, but we would like to also explore more interesting bifurcations, such as Hopf bifurcations, which allow us to investigate transitions between steady states and oscillations, and my personal favorites, the Turing bifurcations, which transition between steady-state homogeneous states and pattern-forming regimes in PDEs. We've applied the model synthesis approach to one model from the synthetic biology fields, but we would also apply it to more models, specifically ones that our group at Microsoft is working with. The repository is GPU compatible, which is nice. I've given you a flavor for what model selection could look like. In situations where you don't know what your functional F should be, it is useful to organize your models and hypotheses in sets of geometrically equivalent or topologically equivalent models. And the way to enumerate that space would probably be using basis function ODEs of some kind, or even neural networks. So there are two main sharp edges in the repo right now. One is to do with calculating the analytical forms. At the moment, I use Mathematica scripts because it's just easier to compute directional second-order derivatives, and then I copy over the code into Julia. Ideally, I'd be using an autodiff way of doing it. Haven't really figured out how to do that yet. The second bit is about regularizing local minima. So there are situations in which the two bifurcations actually land on top of each other and try to match the same target. We need some kind of repulsive term between bifurcations that prevents that from happening. So this is all an experiment. Some things work, some things don't. Yeah, we're working on it. But a bright future awaits in which we can finally design differential equations using high-level constraints. So one of the reasons why Romain's library is so amazing is that you can actually calculate bifurcation diagrams for partial differential equations. And that means that you can specify pattern-forming regimes as targets. So in this case, this is taken from his documentation. There's a 2D Swift-Holmberg equation that exhibits dot-forming behaviors in this region. And simply by using his library in combination with the cost function and everything that I just showed you, you would be able to, in principle, specify a pattern-forming regime in that area. Thank you everyone for tuning in and listening to my talk. I would like to acknowledge everybody who made this possible. Without them, I wouldn't be here. Special shout outs go to Attila and Neil, my two supervisors at King's College and Microsoft Research respectively, who have been very supportive of these crazy ideas. And special shout out goes to Val, who has been an inspiration and absolutely amazing during lockdown and has helped through some difficult times. I would also like to acknowledge the EPSRC-funded Center for Doctoral Training at King's College, with whom I'm doing my PhD. I've met some amazing people there working on a variety of projects, and if you're into interdisciplinary collaborations, then you should definitely reach out to them. Thank you very much.